We're back for Ordination 2 in our final lecture on PCoA in our module on multivariate models. So no required readings, but a really nice optional slideshow on Legendre's version of principal coordinate analysis. So this is really great and goes into a lot more mathematical detail than I'll be talking about here. So if you want more detail, please go check out this link. And as before, we're thinking about multivariate analyses and we're talking about ordination. So, but we're not going to be talking about PCA or NMDS today. We're going to be talking about PCoA. So principal coordinate analysis, or PCoA, is a different type of ordination than we've been doing with NMDS or PCA. So PCA works well for data where it's appropriate to maintain Euclidean distance among objects. However, it's not very clear what to do if you have data that requires a different distance matrix, like many of the distance matrices we talked about previously, or where PCA is not a good model. For example, if you have a lot of zeros or you have presence-absence data. And so principal coordinate analysis decomposes distance matrices, or of course dissimilarity matrices, such that the distance among objects is preserved for any distance measure. So sometimes PCoA is called metric multidimensional scaling, or MDS, because it preserves relationships among objects. And this is opposed to NMDS that does not preserve these distance relationships among objects exactly, but attempts to preserve the relationship among the objects, right? It's trying to think about the relationships of each object to each other. Okay, so let's talk about the steps of PCoA. So first you start with your distance matrix, D, and then you transform the elements in D with to an A matrix, which is -1/2 times D squared. Then you double center the matrix, which means you subtract row and column means from each element and add the grand mean. And this positions the origin at the centroid of the scatter of your data. And then the fourth step is, again, an eigendecomposition, but of this double-centered matrix. And so here, eigenvectors are coordinates for the ordination plot. They do not describe axis of the y variables, however. They only describe distances among objects, sites, samples, etc. And this is similar to NMDS. So let's look at that Sparrow data again, but with PCoA. So let's try looking at our Y matrix of the Sparrow data, but instead of Euclidean distance, let's try Manhattan distance. So if you recall, that's the city block distance. So instead of looking at the hypotenuse between 2 points, it goes, the distance measures up and over like a city block. We use the PCoA function in the late APE library to do this, but I will note there are other options for running PCoA. And so first we create a distance matrix of, again, just our Y variables. So that's everything but the first 3 columns of our Sparrow data set. And we're going to use Manhattan distance. And then we run a PCoA on that distance matrix. And then you can pull out the eigenvalues from your PCoA. And so here you can see these are just some of the columns and some of the rows of this resultant output. And it's just different ways of looking at the eigenvalues that come out of the PCoA. And so you can plot this with this biplot. I find this plot to be not very intuitive to look at, and I apologize for that. I couldn't quite figure out how to plot these well. I don't do PCoAs too often, but I'm sure if you dig around, you could find a much better way to do it than I could. And I did see that apparently you can plot the data on these ordination plots similar to NMDS plots with the NFit, but I just couldn't quite figure that out. So maybe I'll figure it out for your homework, but for now, I didn't quite figure it out. And so with that, it's a really short lecture. So please complete quiz 10.3 on Canvas, and this is the last lecture for this week.